Alright, so I want to go through the official solution for this problem, but I also want to give you some motivation as to how you might come up with a solution, So if you look at this problem, it's actually pretty tricky looking because you don't usually get equations with the x in the powers, okay? Usually the x is in the base. Okay, so this is a strange equation, and I think a lot of you, if you had enough time, might notice that these are all powers of 3, okay? So this is 3 squared is 9. So that becomes 3 to the 2x plus 2. And 2187 is actually 3 to the power of 6. Okay, but because these are real numbers, x,
Power of 6 or power of 7?
7. Oh, maybe it's 7. I can quickly check that. So 3 cubed is 27, 3 4 is 81, 3 to the 5 is 243. Yeah, so it's going to be more than 6. Yeah, 7. Yeah. Okay, so unfortunately this equation has got real numbers. So it's kind of already, when it's real numbers, it's already something I don't consider to be like junior anymore. Okay, real numbers is more like intermediate and senior. So it's a little bit weird. And you can already see like one of the main theorems here. It's called intermediate value theorem. The intermediate is not meant, it's not like junior intermediate, though for practical purposes it could be, but it's just saying that if you have expressions that vary continuously, okay, and this expression is bigger than this expression, right, for some value of x, okay, and then you increase the value of x, and then suddenly this becomes bigger, okay, so this starts off bigger, and this is smaller, and then if you increase x a bit, this turns out to be bigger, and that turns out smaller, right? If that happens, then what the intermediate value theorem is saying is that somewhere in between, they must have been equal. So there must have been actually a solution to the equation, okay? So for example, if you substitute I don't know, x equals 0, yeah? So if you substitute x equals 0, on the left-hand side, you basically get 9 plus 2187, yeah? Which is roughly 2200, yeah? But on the other side, if you substitute 0, you get 1, right? So 2200 is much bigger than 1, okay? Okay, but you could substitute another value of x. Maybe, let's see, what other value of x could you substitute? So at the moment, this is bigger, this is smaller, right? So it seems like it's hard to substitute. If you substitute x equals 1, it's going to be 3 to the 5. So it's going to be hard for the 3 to the 6x minus x squared to get bigger than 3 to the 7, you know? So we need 6x minus x squared to be bigger than 7. You know? Is that possible to do? So we can maybe do x equals 2. Okay? So x equals 2, you get 8, 3 to the 8, right? And 3 to the 8 is bigger than 3 to the 7 plus 3 to the 6, you know? Right? Because 3 to the 8 is 3 to the 7s. And there it's not even 3 to the 7s, you know? Okay, so if you do x equals 0, this is bigger, and if you do x equals 2, this is smaller, yeah? So that means by the intermediate value theorem, and a lot of people call this IVT, but the thing is, if you're talking to people who don't speak English natively, IVT doesn't necessarily strike them as meaningful. So intermediate value theorem. So this intermediate value theorem idea is actually in your high school syllabus as well. Okay, it's just in the HSC. It's one of the principles behind these techniques, like Newton's method and halving the interval method for finding solutions to equations like this. Okay. And especially when you're new to this, I encourage people to try lots of values. So what this tells you, there's a solution for x between 0 and 2, right? Does that make sense? So then halving the interval method, or basically just kind of keep calculating, right? If you do x equals 1, yeah. Okay, x equals 1 gives you 3 to the 4 plus 3 to the 7, and that's bigger, right? So this is bigger. This is smaller, yeah? Okay, so what does that tell you? So that tells you the solution is not just between 0 and 2, it's actually between 1 and 2, right?
You could have the options.
Yeah. So you actually keep going, right? You can do like 1.5. You can actually like, so this problem actually isn't like a exam problem. It's a take-home exam. So you actually have more time. Okay. So you could potentially just keep um getting closer and closer and closer, right? So you won't get the exact value for the solution, but you'll get as many decimal places as you want. Does that make sense? Because you can just try 1.5. Okay. You might not be allowed to use a calculator, but you can still maybe reason which one's bigger and which one's smaller. Okay. Um. Okay. So if you do this, okay, you'll discover that. Okay. So if we use the value 3, yeah. So for 18 minus 9 is still 9, so it's still bigger. Okay. But if you use the value 4, that's 24 minus 16, right? That's 8. But the other side has like a 10, no, 10, right? So if you do x equals 4, this side gets bigger again, right? Yeah.
Yeah.
And smaller. Okay, and what that means is that there's another solution between 2 and 4, right? Because it switches again. Does that make sense? Because x equals 2, it's smaller and bigger. And when you get up to 4, it's bigger and smaller. 3, it's still smaller and bigger. Because 3, it's 3 to the 9. Oh, yeah. So it's actually between 3 and 4. Yeah. Okay. And if you think about it, these are going to be the only solutions. Okay. Because if you keep going beyond 4, like the right hand thing is only going to get smaller and smaller. The other one's going to get bigger and bigger. So they're never going to cross again. Okay. So it's going to stay bigger. The left hand side is going to stay bigger. Okay. And if you look under 0, less than 0, it's also going to stay bigger on the left because it's got 3 to the 7. Okay, the right hand side is 3 to some negative power. Yeah. So basically, these are going to be the only two solutions. So then when they ask you to find the sum of the largest and smallest values of x, you're actually just trying to find the sum of the only values, the only two solutions. Okay. All right. Now, so you're not allowed to use calculators or anything, but if you are diligent, you can actually get quite close to what the numbers are. Okay. So for example, one of them, I think it was like 1.4 something, and the other one was like 3.6 close, something like this. But the point is, if you were very diligent in getting close approximation, you would see that they add up to 5. Okay, you wouldn't know why they add up to 5, but you would see that they do add up to 5, or something very close to 5, depending on how many decimal places you got. Okay, so you might come up with the guess that they add up to 5. Okay, so if you knew it actually added up to 5, it actually becomes kind of much easier to prove. Okay. So it'd be a little bit unrealistic, especially in high school, to actually solve these equations, unless you had a clever trick, okay? So in high school, you're not really taught how to solve these exponential equations. But if you know the sum is 5, maybe you would try to make the equation look symmetric with respect to 5. Okay, so here's what you might do. So if you got 3 to the 2x plus 2 plus 3 to the 7 equals 3 to the 6x minus x squared. Okay, so one thing you could do is you could minus the 2's, so divide by 9, you get 3 to the 2x plus 3 to the 5, okay, 6x minus x squared minus 2, yeah. And then what you could do is you could take minus x from both sides. So you got 3 to the x plus 3 to the 5 minus x equals 3 to the 5x minus x squared minus 2. You know? You see, now you have the 5 in there. Okay. And I guess the whole point of doing this is you want the thing to be symmetric with respect to 5, x and 5 minus x. Okay, so if you have 3 to the x plus 3 to the 5 minus x equals 3 to the x times 5 minus x minus 2, yeah? That makes sense? So if x is a solution, then this is actually a true expression, yeah? Okay, but if x is a solution and y equals 5 minus x, yeah? Okay. Can you see what would happen? If x is a solution of y equals 5 minus x, then this thing here becomes 3 to the y, right? Yeah? This thing here becomes 3 to the x times y, okay, minus 2, yeah? But what's x? Well, if y equals 5 minus x, then x equals 5 minus y, right? So then this x is actually 5 minus y, and this x is 5 minus y, yeah? So the point is, y looks identical to x with this equation, yeah? So basically it's saying that if x is a solution, then y is also a solution. Does that make sense? So if x is a solution, then y is also a solution. Okay. So that actually proves that x plus y equals 5. The solution sum to 5. Because we only have two solutions, right? So we have some solution between 1 and 2. And then the other solution, 5 minus that, is also a solution. Okay, and so that proves the sum of the two solutions is 5. Okay. Are there any questions about that? Yeah, so you have a lot of time to try this problem, and I think it's good to really investigate. I mean, you know that I use a calculator, but you're basically just a calculator yourself, right? It's just it takes longer. Okay, the calculator is really it's not, yeah. Sometimes it's not as fast as you think it is. Sometimes it's really just using the same clever trick you are. Okay. Doing like polynomial approximations and stuff. Okay, anyway, so you guys understand that? Yeah?
But like, if we didn't know, because like we use the answer to build our website, to just struggle for a bit.
Yeah, so I guess that's like you could maybe just stumble across this kind of symmetry as you're manipulating it, you know? That's not unreasonable, but I'm kind of trying to suggest a way for which the answer can't really escape you, you know? And I think this is probably how you'd approach it in real life as well, because A lot of equations in real life are solved by approximation. Um, so you're just subbing in values until you get one's bigger, one's smaller until it changes signs. Okay, and then computers are very good at doing that, right? And yeah, and it comes and it's like piecing the problem together bit by bit, right? So you don't necessarily know how to solve the individual solutions, but if you approximate it, you can sort of see that it sums to five. And then if it sums to five, you might try to come up with something like this to reflect the symmetry with respect to five. Okay. All right.